in the morning session, actually, we left here at this point. So let me discuss a few more details about it before entering into the implementation session, which will be done in the last 15-20 minutes. So I will give a brief review about how to link our neural networks with the partial differential equation. So let me first make this screen. So this is basically the point where I left last time. So here, if you see, as I was discussing that the handcrafted features I was discussing last time. So these handcrafted features are important, and without that, it's very difficult to carry out the task of machine learning model. So this was the case in the case of regression, and this is the case for classification model. So you can see by inspecting the data, then you have to yourself handcraft some of the features, whether it's a linear or a non-linear, and based on that you will be coming up with the hypothesis function, which actually will discriminate between the two classes. So this is actually the drawback of the fixed model based algorithms which we are using in machine learning. So now the next topic that I will discuss is how to why actually we need neural networks. So that is again a motivation also for all of us, that when we have these handcrafted features, then the things are okay. But are there any special or automatic ways of doing the handcrafting of the automatic way of extracting the features from the problem rather than doing it by themselves, by doing it by ourselves? So for that actually comes the idea of neural networks. So here we have this input layer where we feed in the inputs, and then we have these hidden layers shown in green layers, green color. So here you can see we have three layer neural network, and then we have this final output layer which actually gives you the decision based on whether you are doing it for a classification problem or regression problem. So depending upon the type of problem, this node will have different behavior. So this is basically the neural network, and the key takeaway point that why we need neural networks, why we are not doing it with the earlier case of simple machine learning models, is that in neural networks, if you see that if you feed basically a image, like for example, you have this image which is a, let us say, 8 cross 8 dimension image. So the thing is, you cannot feed directly the image itself into the neural network. Actually, you have to flatten it into one dimensional vector before feeding into it. So basically, that's why we have this 64 inputs at the starting of this neural network. So the advantage of using neural network, that why we are using it compared to the other traditional machine learning models which we have, is basically the automatic feature extraction capability that our network has. So that is one of the major advantage of having neural networks coming into play compared to the other machine learning models which we have, because the hidden layers that you have over here, actually it extracts the features which are there in the image. So that is actually one of the key important points in neural networks. So let me show you that first before going any further. So this is basically the slide which actually shows you how the hidden layers are actually having some feature information for this images, set of images which were actually fed during the training time. So for example, here if you see, we have a lot of images we fed it into the neural network during the training process for the purpose of cats versus wolf classification. So this is just showing you a pictorial representation of what is actually happening within the internals of the neural network. So here you can see the first layer actually, if you try to picture the first layer, you will observe that the first layer will have very significant, not significant, very simple features extracted from the images. So you will find most of the edges of different location of the picture, which is you will observe in the initial layer. So it will not be a complex feature extraction. It will be having very simplistic edge based features in the first layer. As you move towards the higher layers, you will observe that these features will be actually combined together to form more complex shapes for the particular animal which you are actually feeding this training example of. So you can see here, tail is appearing in the higher layers. Then you have leg here, then the face of the animal, and then the legs, and then you have this. So basically all the higher layers will be considering, all the higher layers will be having more complex features in their hidden layers, and the lower layers will be having uh, simplistic features in it. So these simplistic features will be actually combined to form more complex features. Finally, in the top layer, you will be able to identify which animal it is. So that is the beauty of using neural networks. So without actually coming up with our own features, neural network itself actually captures the internal details about the features, and it actually uses all these features together to form the top layer. So that is the advantage of using neural networks compared to the earlier case which we had for machine learning. So let me go further, and let me show you a simplistic visualization that how an image is feeding into the into a neural network to generate some prediction. So here you can see image 9 is actually fed as a one-dimensional vector into this network, and then network is doing predictions, and you can see the way it is happening. So here the image is flattened into one dimension, and then it is fed into the neural network to get some prediction. So this is actually showing you some animation for how you are actually feeding an image into a neural network. Okay. Another important thing that we have in a neural network is basically the universal approximation theorem. So here, what that means is that universal approximation theorem says that any continuous function in the range, sorry, this was having some, some problem. So any continuous function f can be approximated arbitrarily well by the neural network with at least single hidden layer with finite number of weights. So basically, whatever be the continuous function, it can be easily approximated by the neural network if you try to use if you use a single layer, a hidden layer with finite number of weights. So any function can be approximated using neural network. So let me show you a picture for this to give you a more insights into what's happening. So here you can see we have a single input X, and then we have multiple units in the hidden layer, and then finally we have some output Y. So what we are trying to say in the universal approximation theorem is that if you have this continuous curve which is shown in blue, so what our neural network will do is it can actually predict the actual curve by doing the approximation thing through approximation theorem. So basically, in a nutshell, what it says is that the neural network can easily using multiple hidden layers, because this is particularly a single hidden layer, that's why you have these blocks of approximation for this continuous function. But if you use multiple such hidden layers, then you will be able to easily predict the blue curve. So what it says is that any curve can be computed using the neural network, so through universal approximation theorem. So this is actually the basis of why we moved to use partial, why we were motivated to use to use this problem of solving partial differential equations or any differential equation using neural networks. So this is the main motivation of uh, going to that area. So the idea of backpropagation is also very important. That is how things are moving around in a neural network. So here you can see this on the left side we have a neural network where you feed in the input features x1, x2. So what it does is like these are all biases which are there on the top. So for now we are not focusing on these biases, but right now on the input. So here you can see if you feed in the input and you make this um, calculation go from left to right till you reach to the final output f, that is basically the term which we call as forward propagation. So in forward propagation, what you are doing is you are actually moving the data from left to right. So so in one step you are actually forward propagating, and once you forward propagate any specific data, the corresponding prediction of that will be actually given by y hat. So the thing is, this is the y hat which is coming from the neural network, and you also know the true value of that y. That is what value this y corresponds to for this x1, x2. So the thing is, obviously, neural network in the initial stages will not be able to predict y hat closely to y. So if it is not able to predict closely the value of y, it will make some error. So that error is actually, evaluated in terms of the loss function. And recall that I have already discussed the loss function in our earlier session. So this loss function is also similar to that. So what we do is we actually do a difference between the y hat and y, and the loss function which you get here will be actually used by the optimizers to do the back propagation, so that you will be, updating the weights which are actually, are there, which are used for connecting the hidden layers. So these weights which are actually connecting the hidden layers are updated based on the optimizer, which actually requires loss function as the input. So the output here is basically the partial derivative of the loss with respect to the weights and the partial derivative of loss with respect to the bias. So all these derivatives will be actually used in the optimizer to update these weights in the hidden layer. So this is actually the scenario which is going on in the backward propagation, and this is an iterative process. And with each image you will be, each image or each data, you will be doing this process again and again, and based on that you will have these weights, set for a neural network. So the typical type of loss functions which we find in literature related to regression are actually mean square error and mean absolute error. So you can use either of them. Some one the absolute one has a subtle advantage over the mean square in terms of its robustness to the outliers, because if there is an outlier, then this particular loss function will actually, work better as compared to this, because if an outlier is there, then the prediction boundary created by the neural network will be affected in this case more as compared to this case. So sometimes we do use L1 loss here, so that to make this boundary coming up with the neural network more robust. And in case of classification, I was earlier also telling you, this is the binary cross entropy, which actually tries to find out the basically the loss function. So this is also one of the loss functions used in classification scheme. So these two will be used actually uh, at this point. So here you will be evaluating y hat, which is generated by the network, and yi is the actual label. So you have to substitute that values to get to the actual score, and you use that score to back propagate to generate the derivative of the loss with respect to weights and biases. Okay, so basically what is happening is, once you have this loss function calculated, so right now it's represented by J, but somehow, like, it can be, it can be L also. So this is the loss function, and the contour plot of this loss function is actually, looking like this. So here you can see, if you are at this point, then in order to go to the minima of this cost function, you have to perform gradient descent, which is one of the fundamental techniques of optimization, though you can use any advanced techniques also, like stochastic gradient descent or Adam optimizer. So there are tons of optimization algorithms which you can use to actually, do this downhill propagation of the points, so that you can reach to the minimum of this cost function. And I told you, if you recall from our earlier lecture, I told you already that reaching to the minima is actually finding out the best decision boundary in terms of the mean square error, or in terms of the loss function which you are defining. So reaching the minima is actually going towards that, and it's a two-dimensional version of, this is a higher dimensional perspective, this is the two-dimensional perspective of doing the weights update. So here theta actually represents the weights and biases of the neural network which are internally connected. So this is related to that, and here you can see we have alpha also, which is a learning rate parameter, and it also plays a very important role, because if alpha is very small, then it will take a long time to actually go towards and hit to the minima, because you are actually subtracting from the old value a very small value, because alpha is very small, so successive steps will be very small. But if your alpha is very big, then your successive steps will become more big, and you will actually reach to the minima faster. But there is a catch here, that if your alpha is too big, then it might be the case that it will miss the minima, because suppose it jumps to this side, and then again, with some maximum alpha, what will happen is it can jump to this side. So it will hit them, it will miss the minima. So that is again a problem. So playing around with alpha is again like a hyperparameter which you do not know that what is the actual value of it, but you have to play around with this so that you can actually solve for that particular problem and get to the minimum value. So there is no direct answer, there is no direct value of this alpha. So this is actually a very basic optimization strategy which is gradient descent. So this is actually showing you that. So it's also called as a learning algorithm for the task of for the neural networks. This is again showing you a training process where uh, things are going back and forth. So when it's going in front, it means it is doing forward propagation, and during the back side, when it is coming back, means it is updating the weights during the process of back propagation. So this is actually showing you the animation for that. Okay, so sometimes you will hear that people are using these type of words like deep learning and some fancy words. So basically, I would like to tell you that deep learning is nothing more than you are using a larger number of layers in the neural network. So basically, earlier when we were using traditional neural networks, we were having one or two layers, but now because in the era of higher computational facilities that we can actually have multiple such layers, multiple hidden layers, which can have, which can give you a huge computational, challenge. But as you already have GPUs, so you can make use of these multiple layers, because we know that the more layers you apply, the more better this deep neural network will become. And some of the other techniques actually like convolutional neural network, which are actually the advanced version of deep learning, advanced version of these neural networks, is basically used to overcome the disadvantage of neural networks. If you see here, in case of neural networks, what we do is we actually convert a two-dimensional image into a one-dimensional vector, and then we are actually feeding it into this neural network. So the problem with that is that the neighborhood information in the images will get lost. So if the neighborhood information of the image patches will get lost, then it's very problematic, and it's not advisable also to convert a 2D into 1D and feed it into the neural network. So that's why convolutional neural networks started it's started coming at that time to overcome this problem, where CNNs directly use images as the input to these neural networks. So three main drivers that actually you require for doing this, deep learning task is the data. That is, you have to have a large data for doing this task of, machine learning or deep learning tasks, and then better models and algorithms to implement or process this data. And again, one of the most important thing which is actually required, and without it, it's not possible to do any deep learning task, is you should have an efficient GPU, graphical processor in it. Without this, it's really very difficult to do even a simple task of doing a prediction of a like if you take images of size 256 cross 256, it will take a lot of time to do prediction tasks. So this is actually the most essential part in, or you can say a driving horse in for doing some deep learning tasks. So, and if you have any questions, please let me know here from these slides. Any questions? Okay. So is my screen visible now? So I have actually changed the slides.
Yes, yes, it is.
Okay, okay.
Yeah.
Okay, so let's change gears and try to do something from this neural network. So uh, if you heard the last lecture also, it was also covering basis of neural network, and they have also given some details about the idea of physics informed neural networks. So that also in short we call as pins. So we are also trying to do that same thing, but I am giving you a very brief overview or motivation, you can say, to begin with. So the reason, actually, the main reason, just a second. So there are actually some reasons that why NN are suitable for solving differential equations. So we want to first understand that before jumping into the problem, because it's very important to understand that whether it is feasible or not without actually, without knowing it, directly jumping into the problem is again not advisable. So these are the three important points which are actually important, which motivates the researchers to use to solve differential equations using neural networks. So the first one is the universal approximation theorem, which I have already shown you in our last slide, where you can actually use basically any curve can be approximated using neural networks. So that is actually a universal approximation in nutshell. So this is the main motivation which actually basically motivated them for solving differential equations using neural networks. The second most important motivation that actually they saw was like the availability of the gradients using back propagation. So this is again one of the most important things that are required for doing the differential equations, because in differential equations we have derivatives, and in the software that we will be using, like for example TensorFlow and PyTorch. So all of these softwares actually have their all of these softwares have their own ways of calculating the back propagation. So once you use a function like backprop, or not backprop, some gradient functions are there in TensorFlow. So once you use them, you will automatically get the derivatives of the output with respect to the inputs. Like for example, if you have a neural network and this is your output y, and you have two inputs, let us say x1 and t1, because this is a differential equation which involves space and time, so x1 and t1 will be there. So basically once you formulate this neural network and do the training process, at that time when you do a back propagation, you will always be available with the derivatives of dy with respect to dx, and dy with respect to dx, yes, and then dy with respect to dt. So these derivatives will be automatically available to you when you do back propagation. So that is again one of the USPs of using for solving differential equations using neural networks, because the software is inherently helping us to provide with all these back propagation values. And the third one is the formulation of the loss function L theta. So this is actually a challenging task, because as I told you, we have three different loss functions in case of regression and classification. So here in this case of neural networks, when you are solving differential equations, the loss function formulation is a challenging task. So once we are able to actually find the proper loss function, then we can easily solve the problem of differential equation. So we will see this, that how we will formulate this loss function, because it's a challenging task. So we will see and understand slowly. And neural networks will be working as an optimizer here, because it will be used for doing this task of gradient descent. So here these are the three important points which actually will be the scholars are motivated for solving differential equations using neural networks. Okay, so this basically shows you a brief understanding of how these differential equations are solved using neural networks. So here you can see we have two inputs, x and t. If you see here, we have two inputs, x and t, and because the differential equation is both in space and time. So basically we have two inputs, x and t over here, and then you have this output u. Right now it's written as u here, but we can take it as y. So what we do is we actually formulate a neural network. So it will have some multiple layers and multiple number of neurons in that. So basically what you are doing is you are actually using this as the network for doing the implementation of differential equation using neural networks. So here what we will be doing later on is that these weights which will be trained during the training process will be actually behaving, or you can say mimicking, the differential equation which we want to actually formulate using the neural networks. So this is the diagram for that. And now comes the important part, which is the loss function. So you please ignore this particular loss function because it is specific to a paper which is discussed over here. But the idea is that we have to come up with a loss function which we will be using for doing this particular process, which is we are trying to minimize this loss function, and we want to find the values of weights and biases, which are actually the weights and biases in the internals of this. So these weight matrices which are there in between the hidden layers. So we will try to actually find the weights and biases that actually minimize this particular loss function, which we will be defining in a second. So this is basically the idea. And once we have these weights and biases, we can actually use for back propagation as I discussed last time. So the new weights and biases will be obtained by minimizing the loss function, and back propagating it will actually update the weights, and slowly we will actually converge to the solution. So this is actually the general idea how to solve differential equations using neural networks. So let us see one small example based on what we have discussed, so that you will get the idea or a clear picture of how to formulate the problem using neural networks. So here I have taken one diffusion equation which is given over here. So here you can see we have a diffusion equation which is given like this, and here you also have the range which is allowed. So x is ranging from -1 to 1, and t is actually in between, is from 0 and 1. So basically this is the allowed range for this particular differential equation, and along with that we have the initial conditions also given for this differential equation, which is this and this. So here you can see we have the equations available for initial conditions and boundary conditions available for solving this differential equation. So they are must actually. I know you all know about this, but this is the actual problem setting which we want to implement using neural networks. So the exact solution, if you try to solve it through various other methods, you will get this answer as the exact solution, which is e to the power minus t sine pi x. So this is just for your reference, but so the important thing is once the neural network is implemented, it should actually follow this curve. So whatever curve it is, it should follow this curve exactly. Then only we will say that the differential equation is implemented using neural networks. So here, the important thing that is to be kept in mind is the challenge is to have a loss function. So if you remember the loss functions that we were using in our case of neural networks, or maybe in the machine learning algorithms, it was involving the prediction from the network, and you were subtracting it with the original label which is available with it. So here actually the problem is very a little different. Here you do not have the original labels along with you. The original labels are there, but they are for selective situations, which I will tell you in a while. But the problem is these labels, which are the original labels, are not available. So what we do is we actually rearrange the PDE in this sense. So here you can see what I have done is actually I have taken all this particular side, right hand side, and moved it to the left hand side. So here you see I have just rearranged it and equated it to 0. So basically once you rearrange it and equate it to 0, it will look like this. So now what we will do is we will actually use neural networks to approximate using the universal approximation theorem, which what we are saying is that the neural network will actually approximate the output yxt. So the yxt, which is actually this one, this yxt. So what I am saying is that the neural network which is over here will actually approximate this output yxt, which is nothing but the output of this differential equation, or the solution of this differential equation. So this is the neural network, which using the universal approximation belief, we are saying that its answer will be very close to the output of the differential equation yxt. Okay, so once we have that, what we can do is we can actually replace yxt by neural network output. So you can replace all these y's through neural network outputs, NNXT. So these are all the outputs generated by the neural networks, and the y is the output of the actual solution, and we are saying through approximation that both are same. So we will replace this differential equation by this and this. So now once you have this, that is actually equal to the earlier situation which we had written. Instead of nn, it is y. and then we have equal to 0. So this is actually coming from here only. So now what happens is, since neural network is a function, so you know a neural network is a function, basically an arbitrary function, so we can obtain its derivatives. If you remember, I told you during the back propagation, we can actually easily get the derivatives of the neural network with respect to time, and we can also get the double derivative of the neural network with respect to time by calling the back propagation command 2 times. So if you apply a back propagation once, it will give you a value here, and then you can use this value again in the back propagation function to get the second derivative. So basically, it's very easy to get higher order derivatives as well as the single derivative with respect to time using the automatic differentiation scheme available in TensorFlow and in PyTorch. So you can easily you can easily use it to get these values. Okay, so actually what we do is now we are planning to define a loss function, which is again, last time I was telling you is challenging in case of differential equations. So what we do is we actually define a function f in such a way. Here you see we have defined the function fxt, which is nothing but the earlier one only, but we are writing it as fxt. So the idea is that if this function actually becomes close to 0, then neural network is actually following the partial differential equation trajectory, because this is already equal to 0, right? So if we are writing it equal to fxt, that means if this tends towards 0, then what we are saying is that neural network is following the partial differential equation with time as the time progress. So to evaluate the partial differential, the important thing now is to define the loss functions. So here, to evaluate the partial differential equations, certain number of points nf inside our domain are to be taken. So we have this domain defined, right? Here we have these domain defined for this differential equation. So what we do is we take certain points inside this domain defined by this particular, x and y constraint. So here, if you use that points and you call them as nf, then what you do is you actually define one loss function like this, which is all the points which are there inside which are defined inside our domain, so that are nf. So you are doing a 1 by nf summation of all these points running from 1 to nf, and then what you are doing is you are actually using this particular fxt, and you are squaring it, and you are feeding the values of xi and the corresponding ti's here. So these values which you are feeding xi's and ti's are actually, when you square them up and sum them up, it's giving you a loss function, which is a mean square error loss function, which is also called as unsupervised loss function. Why it is called as unsupervised? Because the actual labels are not available to us. That is what the challenge is. So this is actually a unsupervised loss function for the partial differential equation. It's not the same as, the one which we were discussing last time, that is y minus y hat. It's not that. So that's why we have to come up with some other loss function. So this is the one which is also called as the unsupervised loss function for the partial differential equations. Next, the training data set is actually, the training data set is also available, and it's a set of points from which we know the answer. So we know the answers from the boundary conditions and the initial conditions. So if you see here, we already know, if you take the points from the boundary condition, if you take the point from the from the boundary conditions here and from the initial conditions here, you know what the answer is, like sin pi x 0 and 0. So you know these values. So if you know these values, then what we do is we select points from the boundary conditions and initial conditions and form another loss function, which is given over here. So here you see, so what we do now is we select NB points from our boundary conditions and NC points from our initial conditions, and use them to form another mean square error for the boundary condition and another mean square error for the initial condition. So here you can see what we are doing now is I am actually summing up for the two conditions here. So if you see, the first one is for the boundary condition. So here what I am doing is, you can see from here, this is the boundary condition. So from this boundary condition, as you know from the approximation theorem, we can replace y with nn. So I am replacing it by nn. and then this is already there, and instead of t, it is tj, and j is running from 1 to nb. So these are the number of points which are there in the boundary condition. And what we are doing, we are actually subtracting the value of the neural network which we are generating, and that has to be equal to 0 actually, from this condition. So whatever values you will get from this answer, it should be close to 0. So it's a supervised type of loss going on over here. So that's why you have this minus this, and you are squaring it to create the mean square error type of stuff. And similarly, you can do for the other thing also, this one boundary condition also. So here you can again write nn instead of y, and then you have tj here, and then minus 0. So you know the answer for all the values of t which you put here. When you take the t in the boundary conditions, then you will get answer as 0. So you have to square and sum them up, and once you square and sum them up and take the average, so you will get a mean square error boundary condition. Similarly, for the initial condition also, you have to do that same task, that is k running from 1 to nc, and then you have 1 by nc is the averaging of the of the cost function which is given over here. So here you see, again I am writing nn instead of y, and then we have the samples xk taken from the yeah, initial conditions. So here the answer for that, it is this. So basically you are actually doing a you are calculating the mean square error in case of, it's a supervised type of loss which you actually normally do in case of machine learnings. So basically what we have to do is, now in order to train the partial differential equation, we have to actually combine all these three losses together, so that then we can actually train our weights and biases of the neural network. And then once the training is done, after that your neural network will actually start mimicking the behavior which the partial differential equation will do. So here alpha and beta, which are actually used for doing the balance of these two terms, are basically either you can tune them by yourself, or you can tune them automatically also using the software, like you have to take the derivative with respect to alpha and beta also. So these things can be made tunable also. So basically it helps in actually uh, that's why it plays an important role in improving the training of the neural network. So alpha beta have to be adjusted properly. So this is the actual loss function. So once you have this loss function with you, then you can take the derivatives of this loss with respect to the weights, derivative of the loss with respect to the bias, and then you can use the gradient descent to update the weights and bias of the neural network, so that you can actually train your network to follow the partial differential equation behavior which is over here. So once you do all this process, then this particular neural network is ready to predict the values, or you can say the trajectory which actually the differential equation will follow. So any questions here related to this? Any questions? Okay. So if you have no questions, then I would ask my student Dhiraj to actually uh, show you a small demo of the differential equation, which actually performs in a similar way which we have done. So the only difference is the differential equation which he has taken is a bit different, but the overall idea which I have discussed here will remain the same. So Dhiraj, are you there?
Ahlad, I think I have one small question. I mean, I think, sorry.
Yeah, please.
Okay. So
Yes, yes.
this, uh, how good are these approximations in terms of, like when we are solving any differential equations, so especially non-linear differential equations, right? So
The
how,
trajectories that we are getting, in terms of the percentage, if you say, uh, it can come very close actually. The more you try to include nonlinearity in terms of the difference, in terms of the neural network, like the more layers you try to add, the more closer you will become to the actual curve which you have, right?
but I think
So
in that case the
depending upon the,
complexity will increase, right?
in terms of the network you are saying.
Yes, 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 yes.
Yeah, complexity, yeah, definitely it will increase. But as you can recall that we have this computational power, right? So this computational GPU is the main workhorse. So even in the other tasks also where we do classifications, complexity do increase a lot when we use large number of layers and different hyperparameters. So there are no specific studies to show that okay, for this problem only these layers will be okay, and for these problems this layer will be okay. So there is no specific study for it. So it's all trial basis. You have to use the layers depending upon your performance, like how good you are getting. So these are all hyper parameters. So complexity do increases if you try to
Okay. So
use more layers.
is there any popular differential equation or something which has been handled by the neural networks right now, or
Popular one?
popular means some
Yes,
famous
yes.
ones like the Navier-Stokes equation? Whether somebody
No,
has
they have used Berger's equation actually. They implemented it in one of the papers by Rising. I don't know the exact name of that person, but he has implemented in his paper a Berger's equation
okay,
to do the things here.
and whether somebody has tried fractional differential equations as well.
I think no. I think still I think that is left. I think
That's a,
that one can
that's
be
a
used. Uh,
yeah, that's a good research problem. That means so.
yes, yes, yes.
Okay, okay.
Okay.
Thank you very much.
Thank you. Thank you. Thank you. So now our student will actually show the audience a particular implementation of this differential equation. So let us see that. Uh, Professor Madhukan, please give the rights to the student so that
धीरज को देना है ना?
yes, yes, yes.
Yeah, he is here only, so I have given him right.
Okay.
Thank you, sir. Good afternoon, all of you. Recently, we have studied the artificial neural network and about that how we can define loss function. So now I am going to implement one tutorial. We know that in differential equation, we solve differential equation by using analytical method. There is some numerical method also available. So, but sometime analytical solution may not be available. We cannot find, or sometime in numerical approximation there is a problem of computational problem. It is difficult to convergence to solution. So after the boom of deep learning, the artificial neural network, by using the artificial neural network, we also, the role of artificial neural network comes in differential equation. And by using that artificial neural network, we are trying to solve, we are approximating our solution of differential equation. So now let's see the one simple example about how to solve differential equation by using neural network. So here I have taken one example. For simplicity, I am just taking here u dash equal to 2x with initial condition u of 0 equal to 1. So, but we know that the analytical solution of this differential equation is u equal to x square plus 1. So it's a simple differential equation, but sometimes it is difficult to solve by analytically. So that time our method will work. So for simplicity, I have taken this. So now we will start to implement how to approximate this solution of differential equation. So first, we need to import some libraries. Here I have imported NumPy as a NP. So NumPy is used for our working on array. And again, I am importing TensorFlow as a TF, which will help in working on tensor. And for comparing the result, I am importing here matplot library.pyplot as a PLT. So I will first explain how to neural network here, which nodes we can use here, and how many hidden layer, okay. And then we will it will be help to understanding. So first, I have taken here one input layer in my neural network, and then taken one hidden layer here, and then taken here another second hidden layer, and then taken output layer here. So in input layer, my x is here x is one real number. So I just taken here in input layer just only one node. So in input layer just this is the one node, and hidden layer I have taken 32 neurons. So here is node 1, node 2, and node 3 up to so on node 32. Again in hidden layer 2 I have taken 32 neuron here, and in output layer I have taken just one neuron. So all these are no, we can say it is node or neuron also. So now let's see, for that we will some define a variable for implementation. So first f not equal to 1, it is denoting our initial condition. Then infimum yes equal to it give one some machine learning number. So I will infimum yes gives us some number. So I will explain it later. It will be helpful in finding the derivative of our neural network. So I will explain later on about infimum yes. Then I have defined a learning rate equal to 0.01, training step equal to 5,000, batch size here is 100, and display step is 500. So now network parameter are n input equal to just 1. So input layer number of neurons. So in input just only one neuron. So in n input equal to 1 neuron. N hidden 1 means there are 32 neurons in hidden layer 1. So just I have defined a variable by n hidden equal to 32. Again n hidden 2 equal to 32 means number of neuron in second hidden layer. And n output equal to 1 means number of neurons in output layer. Now here is one particular example about how to calculate one tensor with that from n input to n hidden. So here it is giving one tensor about range with n input to n hidden with which is following normal distribution here, and selecting random number here. It will be helpful in our training our weight. So now next come to the, we are defining weight in our weight variable. So in weight variable, let's see here h1 is defined as a h1 means here is let's see here our x is entering from that point. And now x is starting to going here to this node, x is going to this node, x is going to this node, and x is going to this node. So here is some weight available. So W1 here, W2 here, W3 here, up to so on, W32 are available here. So our x multiply with this weight and adding some bias, we will get some z here. So for that, I am defining here h1 as a one tensor here from n input to n hidden layer, and it is also selecting as like that values. It is taking which is follows normal distribution and selecting randomly. So h1 is denoting our weight between input layer and hidden layer 1. Here h2 again denoting h2 is denoting here weight between. See here, weight S2 is denoting between all the weights between that all the weights between hidden layer 1 and hidden layer 2. Again, weight between, again out is denoting weight between output and hidden layer 2. So here is just defined by variable out, and again we require some biases also for learning the parameter. We are also, we learn weight and also biases also learn. So I am adding here biases B1, B2, B3 up to so on Bn. Again, I need to add some biases here B1 dash, B2 dash, B3 dash up to so on B32 dash. So, and again I have also trying to add some biases in output layer also. So I am defining here for that B1, B2 out by tensor library. I am defining B1, B2 out as a some biases. Now come to the point, I am going to apply some optimizer. So I am here used one optimizer which is stochastic gradient descent. So for calculating learning the parameter, I have used stochastic gradient descent. So we know that difference between it is a difference between gradient descent and stochastic gradient descent. So stochastic, sometime we cannot say that in general way which is better, but most of the time stochastic gradient descent which will be give in a good way solution. So that I have used as stochastic gradient descent. So with learning rate. So here optimizer is our stochastic gradient descent. Now I am going to create a model. So here is code for creating a multi-layer perceptron. I have explained, but I am again explaining how to multi-layer perceptron is created in Python. So now let's see here. X will be which X I am taking here. X will be one array, which is denoting here. X is defined as like that way. And next, suppose here we will get one tensor, and then now I am going to here after, let's see here, after entering X from from that nodes, X will be going there, going there, going there, going there. So X with after that we have to take one multiplication X with weight and adding bias. So now let's see here, I am defining layer 1. So don't confuse here. Layer 1 means we can change notation also. Layer 1 means Z also. Let's see here. Z equal to like that sum of summation xi wi plus bi. Means it is multiplication of x, entering x with weight and adding some bias, and it's going toward the next node. Okay. So layer 1 means it is a here it is just matrix multiplication of x with that we have defined a weights h1 and then adding some biases b1 here. So again, now after coming to the that some z is coming here, z is another z is coming here, another z is coming here. That z is x multiply with w that plus adding some bias here and come to the point. Okay. So after that, our activation function is comes in role. So in my model, I have used all the nodes with sigmoid function as an activation function. Now after that, defining layer 1, I am, let's see here. So here I am after coming above layer 1, I am using here sigmoid as an activation function. So after applying sigmoid, we will get some output. So apply here on that, we will get some number here, and then applied sigmoid on that number. So that number is also going to this node. That number is going to this node. That number is going to this node, and up to so on going to up to 32 nodes. So similar way for that node, that node, that node. In this way, our activation function distribute our output in all the 32 nodes. So now come to the point. Layer 2 is defined as similarly layer 1. We are taking again multiplication of layer 1 output and weights in S2. So weights in S2 means where all the weights in hidden layer 1 and hidden layer 2, and again I am adding bias B2. So it will gives us two matrix of 32 cross 32 element. So again I am there I am applying sigmoid on all that elements. So here we will get some number, and I am again adding applying sigmoid here up to so on here. So again we will get some output. So after okay. So after here applying sigmoid, we will get some output. Again that output will distribute towards our output nodes. Now I am defining again output output as a here. Suppose we will get some here output, here will output after applying sigmoid here. So again some weight also available here. So multiply that output with weight and add some bias. So for that just use this code and apply again in last layer also sigmoid apply. So how there is one question about So why I have used sigmoid in all the nodes. So we will discuss in after the implementation. So this is the we have created our one model, which is artificial neural network, or we can say multi-layer perceptron. So now by using universal approximator, let's say we are defining here g of x, which will be approximate our solution. So g of x is like that, x into neural network, x into neural network plus initial condition here. So let's see, g of x is defined as x into multi-layer perceptron x plus f naught. Again, we know that here is f of x. So in our, let's see here, u dash equal to 2x. So our f of x equal to 2x. So I am defining here f of x as a 2x. Here is f of x equal to 2x. Now we have defined a g of x. It will be, I am defining g of x because it will be helping to finding the loss function. So custom loss will be as follows. So here is, let's see here, L equal to positive square or root of summation derivative of g with respect to t minus f the whole bracket square upon 10. So I have taken 10 here. So this is the one average mean. So why I am using this, why I am taking this 10 only? Because I am selecting just 10 points for training our loss function. So let's see about that, how we can create loss function. So our for x belongs to -1 to 1. So let's see here, x in numpy dot line pace -1 to 1 10. So it's saying that we are taking x belongs to -1 to 1 interval, and we just taking 10 points, not whole interval. We are just selecting 10 points. Again, after that, we are defining DNN as a one derivative. So that derivative of DNN means derivative of our defined g. So DNN equal to this term, all this term. Okay, so here DNN means derivative of this g of x function. And then we can define as a, by using append function, we can sum that, and by using reduce mean, we can take average of that loss function. So all the we are defining here loss function. Now come to the point training the function. So let's see here, we again define one train function, which will be help us in for calculating gradient. So I am just giving you one role of this function. So what is the role of gradient type? So the role of this function is to finding the gradient of our loss function. So here we have defined a loss function L, and this function which will be helping finding the gradient of L with respect to trainable variable. So our trainable variable is, you know that in our model. Second. Okay. So trainable variable is, let's see here. Here is some weight, here is some weight, some weight, some weight. Again, here is some bias. So our trainable variable is our weight and biases. So we are taking the gradient of L, taking the gradient of L with respect to all the training variables. So by using this code, we are by using trainable variable, we just here collecting the all the trainable variables. So list of weight values plus list of bias values. So this is giving us to all the trainable variable weight and biases. Now defining gradient here, gradient of loss function with respect to all the training variables. So and after that applying some optimizer, which is we have already defined here. Optimizer is our stochastic gradient descent. So after applying stochastic gradient optimizer, we will get we will try to learn the parameter weight and biases. Now come to the point training the model. Now our main main point is to training our model. So let's see here for I in range training step. So training step is already defined here. Training step is 5,000. So our I is in range of 5,000. Okay. So and train time is calling from that point, that cell 13. So train step is already defined. And now I am after the implementation, we here is we will print the loss of after 500 500 steps. So first loss, this loss is denoting that we will get loss after we have got loss after the 500 steps. Again, this loss is this loss is for 1000 steps. Again, up to so on, we have got loss after the 500 after 5,000 steps. So first is 1.5 1.58, again that loss is 1.1, again 0.9, up to so on 0.94. So loss will be decreasing. So after increasing the step, our loss will be decreasing. So we are finding the optimum loss here. So now our model is trained here, and now our model machine was learn about parameter W and biases. Now we start to compare our result. So plotting the result, first we defined a true solution, which we know that analytically the true solution is defined as defined true solution x as a x square plus 1. So we know that already here u equal to x square plus 1 is true solution. So this is the true solution. So I just here defined a x square plus 1 as a true solution. Now again I am selecting x is x belongs to interval 0 to 1. So from that point to that point, and I am just taking here 100 point now for comparing our result. And this result is denoting our it is for our this result is for our value of finding g at 100 point. So again this is g, we want to find g at this 100 points. So our result is equal to our value of g, and S is our, now again I am defining S equal to true solution at a point x. Now we will plot x versus result. So result is value of g. Okay, that g is here. So result is equal to g at that selected 100 point. Okay, so now we are going to plot x versus result and x versus our true solution. So let's see here the true solution. Let's see the first orange curve. Orange curve is going like that way. So this is our actual solution, analytical solution. And now our approximate solution is blue curve, which is going to like that way. So after let's see here, compare this both the result at, let's see here, 0.0 to 0.4. So solution is as compared to the analytical solution, both the solution are similar. And after that some little bit difference is increases, loss will be maximum here. So in this way we are going to always try to solve differential equation by using neural networks. So this is the end of implementation of our simple differential equation. So this we have solved this differential equation by using neural networks. If there is any question, let me know.
Yeah, participants, if you have any questions from related to his presentation. Okay, I hope you have got all the things. Source change. Okay, so let us thank to our TA and his mentor. Professor Ahlad.
Thank you so much. Thank you so much, Professor Madhukant.